Welcome to the deep dive. Today we're taking a look at something really central to robotics and AR, visual SLAM.
Right, SLAM. Simultaneous localization and mapping.
Yeah.
How machines, well, how they see and navigate the world.
Exactly. You know, if you've seen a robot vacuum cleaner mapping your room, or an AR app sticking a virtual sofa in just the right spot, that's SLAM doing its thing.
It's the tech that gives them that sense of space, that spatial intelligence, using cameras typically.
But getting it right is tough. I mean, the real challenge, the kind of ultimate goal, is getting SLAM that works in real time.
Fast enough to react.
Creates a dense map, so lots of detail, not just sparse points.
Yeah, a full picture.
Works with a single camera monocular SLAM.
Which is harder, definitely. Less information.
Handles basically any environment, so really in the wild.
Unpredictable places, yeah.
And this is key, does all without needing you to know the camera specs or calibrate it beforehand. You know, proper plug and play.
Yeah. And that combination, that's the holy grail. Traditional methods often, well, they stumble. They might need calibration or multiple cameras, or they give you sparse maps, or they just get confused by depth and motion with only one viewpoint.
It's a really hard set of constraints, which brings us nicely to the research we're digging into today, a paper presenting MASt3R-SLAM.
Exactly. This paper proposes a pretty novel approach to dense monocular SLAM, aiming right at those plug-and-play in the wild challenges.
So our mission today is to unpack this. What makes MASt3R-SLAM tick? What's the core innovation here?
And explore the clever techniques they're using, because it seems to be pushing things forward, especially for uncalibrated, real-time, dense mapping.
Okay, let's get into it. The name itself is a clue, right? Built bottom-up for MASt3R, a 2-view 3D reconstruction and matching prior. So it's built on this thing called a prior.
Yes, priors are fundamental here.
Yeah.
See, figuring out the 3D world from flat 2D images is, well, it's an inverse problem. You don't have enough data in the image alone. A prior is like extra knowledge or assumptions you build in to help solve it. Like assuming surfaces tend to be smooth or objects have typical shapes.
Like knowing gravity exists helps predict where a ball will land, even if you only see part of its flight.
Precisely. Now, SLAM has used priors before. Some use single-view priors networks, guessing depth from one image. But the paper points out a single image is, well, ambiguous.
Lots of 3D shapes could look the same in 2D.
Exactly. And predictions from one angle might not match predictions from another. They lack consistency.
Okay, so single-view priors have limits. What about using multiple views?
Right, multi-view priors. Things like optical flow, tracking pixel movement, or multi-view stereo, trying to build 3D from several shots. But optical flow struggles to separate camera motion from actual scene movement.
Did the pixel move because I moved the camera or because something in the scene moved?
Exactly. And multi-view stereo usually needs you to already know the camera poses pretty accurately to work well. So you're kind of chasing your tail.
You need other info to make sense of it.
Right. The insight here, the thing MASt3R-SLAM builds on, is leveraging a different kind of prior, one based directly on 3D geometry because, well, the 3D structure itself doesn't change when the camera moves.
Okay, makes sense. And that brings us to MASt3R, this 2-view 3D reconstruction prior. What does that do? This sounds like the core innovation.
It really is the foundation. So networks like MASt3R-K or its predecessor DUST3R, they do something pretty remarkable. You feed them two images, could be any two images of a scene.
Just two pictures.
Just two. And they output dense 3D point clouds for both images, a whole cloud of 3D points representing the visible surfaces. And this is crucial. These 2 point clouds are generated already aligned in a single common 3D coordinate frame.
Well, hold on. So from just 2 images, it spits out detailed 3D geometry for both, and it tells you how they fit together in 3D space instantly.
Well, not instantly. The network inference takes time, but yes, that's the output.
Yeah.
It's fundamentally different from just predicting depth or flow.
That feels like a massive head start. That's the aha moment, right?
That's exactly it. As the paper highlights, this unified 3D prior essentially tackles several hard SLAM subproblems all at once, implicitly. Finding correspondences between pixels, figuring out the relative camera pose, understanding the camera projection model, getting the dense geometry. It's all bundled into that initial 3D output.
So instead of solving each piece separately and maybe making errors along the way, you get this rich, dense 3D starting point. That is a different approach.
It changes the game for what the SLAM system itself needs to do. But, and this is important, the paper is upfront. These MASt3R predictions aren't perfect. They can have noise, inconsistencies, maybe the scale isn't quite right.
Sure, it's still a prediction from a network, not ground truth.
Exactly. So the real innovation of the MASt3R-SLAM system isn't just using the prior, it's how they cleverly process and refine these potentially noisy 3D predictions to get robust real-time SLAM. They've built specific components for this.
Okay, so the prior gives a strong starting point, but the SLAM system built around it is where the magic happens for making it work reliably. Let's break down those system components. First up, matching points between frames. Dense matching is usually slow, right?
Oh yeah, painfully slow. Comparing every pixel to every other pixel, that's quadratic complexity. Not good for real time. Even MS3R's own internal matching isn't fast enough for a live SLAM system.
So what's their trick for speeding this up? Because they need dense matches to leverage that prior.
They propose this really smart, iterative projective matching. The key idea is they don't assume a standard camera model, like a pinhole camera with known parameters. Instead, they use the dense point map itself, the 3D points from MASt3R, to define the camera's projection implicitly.
How does that work? The point map tells you the 3D location for each pixel.
Right, which means for any pixel, the 3D directional array from the camera center that corresponds to that pixel. Think of the point map as defining a unique, potentially complex generic camera model on the fly.
Okay, so each pixel has an associated ray direction from the point map.
Exactly. Now, to find a match for a point from image A and image B, they take the 3D point from A's point map, transform it into B's viewpoint using an estimate of the relative pose.
A guess of how the camera moved between A and B.
And then, instead of searching pixels in image B, they search for the pixel in B whose ray points towards that transformed 3D point.
Ah, so they're aligning rays, not just pixel patches.
Precisely. They iteratively adjust the pixel location in image B to minimize the angular difference between its ray, defined by B's point map, and the direction to the transformed 3D point from A. It's inspired by techniques for calibrating these generic cameras.
And because it uses the point map's rays, it doesn't matter if the camera is zooming or has weird distortion.
Exactly. It inherently handles generic central cameras because the point map is the camera model at that moment. It doesn't need predefined parameters.
That sounds really flexible. Is it fast enough?
That's the kicker. They implemented this on a GPU, and they claim it takes just milliseconds per image pair. Orders of magnitude faster than traditional dense matching, or even MASt3R's own generation process. This speed-up is what makes using these dense priors feasible for real-time SLAM. Plus, it's less biased by the current pose estimate. They also do a little feature-based refinement at the end using MASt3R's features.
Milliseconds. Okay, that's huge. That unlocks using these dense maps in real time. So once they have these fast, dense matches, how do they actually track the camera's movement frame to frame?
Right, that's the tracking part. They estimate the current frame's pose relative to a nearby keyframe, reference frame where they've built up a good local map.
And how is their tracking different, given they have these dense point maps?
Again, they avoid relying directly on the potentially noisy 3D positions. Many traditional SLAM methods try to minimize the 3D distance error, how far predicted 3D points are from observed ones. But if the depth prediction from the prior is off,
then the 3D point could be way off, even if the direction is right, and that could mess up the pose estimate.
Exactly. A small depth error can become a huge 3D position error, pulling the optimization the wrong way. So, MASt3R-SLAM, similar to their matching, minimizes a directional ray error for tracking too. They find the pose that best aligns the rays from the current frame with the corresponding rays from the keyframe.
Ah, minimizing the angle between rays again. Why is that more robust here?
Because the ray direction is much less sensitive to those depth errors. If the MASt3R gets the depth wrong but the pixel location right, the ray direction from the camera center is still pretty accurate. This makes the pose tracking much more robust to noise in the 3D prior. Angular errors are also nicely bounded, unlike 3D errors which can explode. They do add a tiny distance term just to handle cases of pure rotation, but the ray error does the heavy lifting.
Okay, robust tracking using ray error. Makes sense. How do they build the map itself then? Are they just storing these keyframes?
They do something more sophisticated, local point map fusion. When a new frame is tracked successfully against a keyframe, they don't just store it. They use its information to update the keyframe's point map.
Update how? Averaging or something?
Essentially, yes. They filter the new points and merge them into the keyframe's existing dense point map using a running weighted average. Points that consistently appear across multiple views get stronger weights, reinforcing the reliable geometry, while noise and outliers tend to get averaged out.
Ah, so the keyframes map becomes a refined, averaged version based on multiple viewpoints over time.
Exactly. It incrementally improves the quality and the coherence of the local 3D map around each keyframe. And here's a neat side effect. Remember how the point map defines the generic camera model?
Yeah, the rays.
By refining the point map through this fusion, they're also implicitly refining the estimate of the keyframe's camera model itself over time. It's a clever way to improve both geometry and the camera understanding without needing explicit calibration. It leverages information from all frames locally without storing everything.
Wow, okay. That's clever, improving the map and the camera model together through averaging.
It leverages the density of the prior really well.
So we've got fast matching, robust local tracking, and this clever fusion for local maps. But SLAM systems drift over long distances, right? How do they handle global consistency, the map staying accurate over the long haul?
Right. That's where the graph optimization backend comes in. As the camera moves, the system creates keyframes, and tracking provides links, or edges, between them in a graph structure. But small tracking errors add up sequentially. That's drift.
The map gets warped like stretching a rubber band.
Precisely. To fix this, they need loop closures, recognizing when the camera returns to a previously mapped area. They detect potential loops using image retrieval based on the learned features from MASt3R itself, adapting an existing method called ASMK to work incrementally.
So MASt3R's features help find candidate loops quickly.
Yes. And if a candidate image looks promising, they use their fast iterative projective matching again to see if there are enough consistent matches to confirm it's a real loop. If yes, they add a loop closure edge to the graph, connecting the current keyframe to the much older one.
Okay, so the same efficient matching verifies the loops. Makes sense.
With this graph containing sequential links and loop closure links, the final step is back-end optimization. The goal is to adjust all the keyframe poses and implicitly their fused point maps simultaneously to make the entire map globally consistent.
How do they optimize this whole graph without it taking forever?
Again, they rely on the ray error metric, minimizing it across all the matches represented by the edges in the graph. For the optimization itself, they use an efficient second-order method called Gauss-Newton, implemented using techniques like sparse Cholesky decomposition that are really fast for the kind of sparse graph structure you get in SLAM.
So, a fast math technique tailored for these sparse problems. Does it handle the scale ambiguity? Monocular SLAM can't know the true size of the world, right?
Absolutely. That's inherent in monocular vision. Their optimization handles this gauge freedom, the scale, and overall pose ambiguity by simply fixing the pose of the very first keyframe. Everything else is then optimized relative to that fixed starting point, giving the map a consistent, albeit arbitrary, scale and origin. Analytical derivatives and parallel implementation help make it fast.
Got it. So a complete system, fast matching, robust, ray-based tracking, and fusion locally, and then a global optimization using the same principles to tie it all together and correct drift.
That's the architecture.
Yeah.
It's built logically around maximizing the benefit of that initial MASt3R prior while being robust to its imperfections. It's quite different from end-to-end learned systems.
You mentioned earlier one big advantage was flexibility, especially with the camera. Can you expand on that? That sounds crucial for in the wild.
Definitely. Because the core system relies on that generic camera model defined by the point map's rays, it doesn't need to know the camera's internal parameters, the focal length, distortion, etc. It can implicitly handle changes, like if the camera zooms during capture, or if it has significant lens distortion that wasn't calibrated out.
So you could, in theory, just pick up a random webcam or phone, and it should just work, without a calibration step.
That's the goal. And the paper shows some impressive results, like handling extreme zoom variations where traditional calibrated methods would likely fail. This is a huge plus for ease of use and robustness in unpredictable scenarios.
That really lowers the barrier to entry. What if you do know the calibration, though?
Good question. They show that if calibration is available, you can make a simple modification. Since you know how the camera projects 3D points, you can use the standard pixel reprojection error instead of the ray error in the optimization. When they do this, they actually achieve state-of-the-art accuracy on some standard benchmarks that assume calibrated cameras, like TUM.
So it's flexible enough for unknown cameras, but can also leverage calibration for potentially even better accuracy when available. That's smart.
Best of both worlds, in a way.
And performance. Does all this run fast enough?
They report real-time performance, around 15 frames per second, which is definitely usable. And the results look really strong. On various standard datasets, TUM, 7 scenes, ETH3D, Euro-C, they show pose accuracy that's state-of-the-art or very competitive with top methods.
Including that droid SLAM you mentioned.
Yes, they show favorable comparisons, often outperforming it, especially on pose accuracy in some challenging sequences. But where MASt3R-SLAM really seems to excel, according to their results, is in the quality of the dense geometry. The 3D maps look significantly more detailed and accurate than what Droid-SLAM produces.
Ah, so the benefit of starting with that dense 3D prior really shows up in the final map quality.
It seems so. That's a key takeaway. The paper's analysis also backs up their design choices: the fast matching, the robustness from ray error, the benefits of the fusion step.
So summing up the performance. Real-time, great pose accuracy, handles tricky cameras, and produces really high-quality, dense maps. Sounds like a win.
It's a very compelling package. Of course, they do mention limitations. The MASt3R prior network wasn't trained on tons of images with extreme fisheye distortion, for example, so the initial 3D guess might suffer in those cases, even if the SLAM system tries to cope. Also, while local geometry is fused, they suggest future work could involve optimizing the full global geometry even more explicitly in the back end. And the initial MASt3R inference can still be a bit slow if you need to run it very frequently.
Okay, so still room for improvement, like any research. But the core concept seems solid.
Absolutely. I think the main contribution here is showing a really effective way to build a dense monocular SLAM system differently. Instead of learning everything from 2D pixels up, they start with a powerful pre-trained 3D geometric prior from MASt3R.
And then build a robust real-time system around processing and refining that prior.
Exactly. Achieving great results, especially on geometry, and handling those tough, uncalibrated, in-the-wild conditions. It offers a distinct architectural choice compared to systems like Droid-SLAM.
Which really makes you wonder, doesn't it? What does this mean for the future? Could this idea, building complex spatial AI systems by leveraging these increasingly powerful pre-trained 3D foundational models as priors, become the dominant way forward?
Instead of trying to learn everything from scratch for every specific task?
Yeah. Could it simplify things? Make robots and AR just work more reliably in messy, real-world places? It feels like it might be a really powerful paradigm shift, something to definitely keep an eye on.
It's a fascinating possibility. Shifting some complexity into these base models and then building robust systems on top. It certainly presents a strong argument for that approach.
Indeed. Plenty to think about there. Thanks for walking us through MASt3R-SLAM today. Really interesting stuff.
My pleasure. Always fun to dive into these innovations.